Hello everyone, my name is Mariia Chizhikova, and in this video I'm going to present the contribution of the SINAI research group to the LivingNER shared task at IberLEF workshop held on September 2022. The introduction of electronic health records as the main way of registering patients' medical history created new opportunities to impulse research and development of biomedical technologies. The fact that clinical narrative has free text form makes the extraction of clinically relevant features from raw text data an essential step to leverage it. The first LivingNER subtask brought the community effort to design clinical coding systems capable of correctly identifying both human and non-human species mentions, while the second subtask required normalizing these mentions by assigning each one its corresponding NCBI taxonomy code. Our team participated in the named entity recognition and normalization tracks, and before introducing our approach to this, I would like to make a quick overview of the LivingNER corpus, just to highlight the particularities that motivated our choices of methodology. LivingNER corpus is a collection of 2,000 clinical case reports annotated with quite diversified species mentions, such as human, animals, plants, and microorganisms. Training texts were annotated with 3,006 unique entity mentions that were mapped to 887 unique NCBI taxonomy identifiers, while the validation set contains 1,704 unique mentions mapped to 559 different NCBI taxonomy identifiers. The test set contained 500 texts. Considering that the main objective of the first LivingNER subtask is retrieving both human and non-human species mentions from AHRs, corpus annotations also specify a label for each entity, which could be species or human. As shown on this slide, the dataset is quite balanced in this regard. Another highly relevant characteristic of LivingNER corpus is the length of the text, which in most cases exceeds the maximum length of input for the transformer model we had chosen as the core part of our system. As you can see on the slide, the average length of the text in both training and validation set is more than 512 tokens. This fact brought us to develop a sentence-level named entity recognition system based on fine-tuning and pre-trained language models. Thus, the preprocessing consisted in splitting the text into sentences with the sentence recognizer from the spacey processing pipeline. As for the core elements of our system, we carry out 3 experiments testing RoBERTa models pre-trained on general, biomedical, and biomedical clinical corpora. All 3 models were fine-tuned for token classification task by adding a linear classifier layer preceded by a 0.1 dropout layer on top of the original architecture. For the named entity normalization task, we developed a sequential systems that combined exact and fuzzy string matching between entities and the taxonomy terms. Firstly, we linked all entities that were assigned human label in the previous step to the 9606 code. Then we performed exact string matching between the detected entities and both the original taxonomy and its Spanish translated version. In the third step, the system performs exact string matching against the entities in the training and validation sets. The unmatched mentions are then encoded into numerical vector with term frequency and verse document frequency in order to get most similar terms by calculating cousin similarity with TF-IDF encoded taxonomy descriptions. Finally, all remaining entities were tagged with codes if the Levenshtein distance between the mention and the code description was greater than 0.95. All entities that remained uncoded were assigned the no-code labels as the mentions that are out of the NCBI taxonomy scope. All the transformer models were fine-tuned on a single NVIDIA Ampere A100 GPU by making use of the Hugging Faces transformer Python library. To yield better performance out of our systems, we performed hyperparameter optimization powered by the Optuna framework. You can find more details on the selected parameters in our system description paper. As for the results, our team submitted a total of 3 runs corresponding to systems based on the 3 different pre-trained models: general domain, biomedical, and biomedical clinical. Metrics prove that general domain pre-trained model has a remarkable cross-domain potential, as its performance, despite of being the lowest of all our systems, is still better than the mean values among all submitted runs. The highest F1 scores were shown by the medical model, as you can see on the table. Thank you for your attention. This was the presentation of the SINAI research group at SEPLAN 2022.